I will be presenting our work, Inference of Error Specifications and Bug Detection using Structural Similarities. This is a work of static analysis to detect error checking bugs. And there are three types of error checking bugs that we are interested in: incorrect checks, missing checks, and propagation bugs. So an example of an incorrect check comes from this snippet of OpenSSL, in which we have a function call run the bytes x, and we compare the result with 0. If it's less than 0, we jump to an error path. However, if you were to look at the implementation of this function, you can notice that 0 is also a possible return value. And in this case, the error path is not taken. Second example for missing check is this snippet of code in which we have two function calls, XML start element and XML end element. But notice that the second if check doesn't actually do anything because the assignment of redfall is missing. Finally, propagation bugs. These occur when we have different data types to propagate errors with, but the valid values between the two types differ. So when an implicit or explicit cast happens, the propagation is incorrect, and so any error checking that uses these values can be incorrect. To know how to detect these issues, we first need to know how to model errors. So I consider two broad categories in our work, either model errors by convention or by specification. So convention-based approaches use the fact that error handling code often uses null, einval, go to error, those typical kind of keywords. Specifications, on the other hand, create like a list of functions that can return errors and what the possible error return values for those functions are. So for malloc, this is 0. For open, this is -1. And finally, ZenGetPropertyInfo has two possible values depending on the error condition. Specifications will be what I will focus on. And either you can create these semi-manually or fully automatically. So a state-of-the-art as error specifications is easy, which is semi-manually. It starts with domain knowledge that the programmer needs to provide, and then it expands the knowledge. Automatic approaches are like Apex, ARES, and our approach, ESSS. To illustrate how these kind of work, I'm going to show a lot of code. And I know this can be overwhelming, but it will show my points. Because for us humans and for convention-based approaches, it's still very easy to notice all the error handling codes. Like ERR raise is probably short for error raise. We have a null check, you go to error, and so on. However, this can be very specific to the code base you're working with. Our approach, on the other hand, uses similarities. And to illustrate that, let's take a look at, for example, these two code segments. And we're going to simplify them. We're going to create like a summary of them, a simplified representation that does away with the control flow. The first code segment has a call to arrays and returns 0. The second code fragment calls arrays also, calls another function, and then returns 0. Notice how in the original source code that it returns red, but our tool deducts that at this point only 0 can be valid for red. If we now compare the two summaries, we can see that they both call the same function and return the same value. In fact, you could say that the first one is a subsequence of length 2 of the second one. Similarly, if you take a look at the bn null error handling code, we can see that, well, they both jump to the same label, so the tail is the same, and we again have a subsequence match of length 2. So what's the idea here? Well, we notice that all error handling code is more similar to each other than all the code around it. So the idea is that we create these matches. The best matches are marked as error handling blocks, and once we know what the error handling blocks are, we know what values they can return, and so we know what the error returning values for the functions are. However, this is not enough on its own, because take a look at this example. So we call a function, compare it with 0, and then call error raise. But there's only a single check. There's no similar code to compare against. Fortunately, though, we do see the error raise function again. And the idea here is that, well, if you notice during similarity matching that a particular function is often occurring in error handling codes, and we don't yet know the purpose of some other codes, but we do see a typical error handling function in it, then the code is probably error handling related. So that's basically using association analysis to overcome this problem. A very similar problem occurs when we have like a call, a check, and then there's no other call that can tell us the purpose of the code. However, if we already inferred that malloc returns 0 on failure, then we can easily conclude that f must return -1 on failure. So the entire pipeline starts with LLVM bitcode. We perform the similarity matching that creates an initial set of specifications. Then we apply the two techniques that we've discussed, and that will give us a new set of specifications. Then we repeat the process until we eventually reach a fixed point, and once we have the specifications, we can use that to detect violations thereof. So we applied this technique on 7 different open source projects, so OpenSSL, OpenSSH, the PHP interpreter, zlib, libpng, freetype, and libwebp. We got a lot of reports from them. Most reports are from OpenSSL and PHP because they are also the largest code bases. If you then take a look at the split between missing check, incorrect check, and propagation bugs, you can see that most bugs are missing check bugs. However, personally, I find incorrect checking bugs the most interesting case because they are a lot more subtle to catch. Finally, what we did is we looked through every report and manually categorized them in false positives, true positives, and unknowns. The unknowns is simply a fallback category for when we did not have enough domain knowledge to confidently say if it's a true or a false positive. Then we obtain these results, so not a lot of unknown cases, first of all. Second of all, we notice that the highest false positive rate is for OpenSSL, and this is because of a particular coding pattern in the OpenSSL code base, in which we often have first a function call that performs some validation of the parameters. Then we repeat the function call to do the actual work. So, and in this case, only the first function is actually error checked and not the second one. So every time that pattern occurs, the second one is incorrectly marked as a missing check bug. Second highest false positive rate is for PHP, followed by zlib. All the others are below 25%. In practice, we noticed that it's relatively easy to go through the reports, even with a false positive rate of 25%, for example. We also took a look at how well we performed in terms of memory usage and time usage to infer these specifications when compared to state-of-the-art Easy. First of all, Easy is already very fast. It can analyze OpenSSL in about 3 minutes with only 20 gigs of memory. Notice there's a dash for PHP in the table, and that's simply because the program Easy went out of memory even on a 128 gig machine. So it does show some scalability limitations. On the other hand, our tool, ESSS, uses an order of magnitude less time and less memory. So we were actually able to fully analyze PHP. And if you take a look at the bottom 4 rows, you will see that they have been analyzed with less than a second. So that makes our tool an ideal candidate to, for example, integrate into an IDE plugin in the future so that programmers can actually get feedback at the point they're writing the code. So the results, we inspected 827 bugs in 7 projects. 541 of those inspected bugs were true positives, and we sent patches for 46 of the most severe bugs in 3 different open source projects, and all of the patches have been accepted into the upstream. It amounts to 16 fixes in OpenSSL. Most were incorrect check bugs there, 1 fix for OpenSSH, and 29 fixes for PHP, including 1 bug that got a CVE. There's much more experiments and details in the paper. It's also fully open source on GitHub, and the artifact is fully evaluated. So if you want to play with it, you can just check out the source, and it's relatively simple to get going with it. Artifact evaluation should be, the artifact repository is already online, so if you want to check that out, you can do so as well. So that's it for me now, and I think we can go to the questions now. Thank you.